Hi there, Engineering Physics 2. Thanks for watching today. I'm always happy when I get to come to you, even if it's on YouTube. So thanks for tuning in, and I'm glad to be here. I hope you have some fun, socially distant things planned for this weekend. Well, let's get right to it. Let's talk about current density. Okay, so current density it's like current, but it's actually a vector. Okay, so let's start with the integral of I equals J dot dA. Okay, so J dot dA. J is a vector, and dA is also a vector as well. So let's draw a picture here of our wire. And let's say our wire sort of changes diameters here, okay? Because this is a really important thing to be aware of. When you turn on the lights, so when you push the light switch, an electric field travels through the wire at close to the speed of light. So that means we have some electric field inside of our wire here, okay? That electric field doesn't change, okay? It's constant in here, but it does change if the diameter of your wire changes. So here we have some area right here. So everything, if we took a cross section of our cable there, then it would change. So in this integral, dA is the differential cross section area perpendicular to the plane. So I can also draw another area over here. Okay, so these would be two different areas. There we go. Okay, so one area is much bigger than the other, and if our current density remains constant, we can move this outside of the integral. Okay, so let's do this integral here. Let's say I is going to equal J then dot dA. The integral of dA is just going to be A. So we will have J times A equals I. So what we get out of all this is that our current density is equal to I divided by A. Okay, so that's the current divided by the area here. So if we look at our section here, we have two different areas. There's one right here, and then there's another one over here. Okay? So my current density is going to be different in these two locations because one has a very big area, and the other one has, this one has a bigger area, this one has a smaller area. Those are going to be different. What also changes is the electric field concentration. In this area right here, where we have a smaller wire, the electric field is going to become more concentrated. So, but at the same time, the current everywhere in our device is going to stay the same. So if I'm looking at my wire here, then this is the smaller area. Now, the same amount of current is passing through right here as it is over here. The current doesn't change, but the current density absolutely does change. So for example, if this is area 1 and over here is area 2, then I can say that J2 is going to be much higher than J1. But if I look at the current flowing through here, so this will be, we'll say the electric field is going this direction. So this is my electric field, then my current will be flowing this way. So we'll have I1 here and I2 over there. Well, I1 and I2 are the same. So I1 is equal to I2. Then the electric field is not the same. So it's much more concentrated right here where it's smaller. So in that case, E2 is going to be much greater than E1. Okay, so that's the difference between current and current density. Current doesn't depend on the size of the wire. Current density does. Now let's talk about something else. Let's talk about velocity of the electrons inside of a piece of metal. Now electrons are moving very quickly in the metal. In fact, the electrons can move upwards of 10 to the 6 meters per second between collisions. But remember, electrons inside of a piece of metal often undergo many different collisions with the nucleus of atoms. So let's do a little illustration to better represent my point. Alright, so let's draw a crystal lattice. These are going to be the atoms inside of my solid. And we said that in a conductor, electrons are in a free electron gas, meaning they can move around very quickly. So as the electron is moving around, it's moving here until it undergoes a collision, then it will go over here and it will bounce back. And it will keep colliding like this basically forever. So in between collisions, we can write a velocity here. This is the instantaneous velocity of the electrons. But on average, when we apply a velocity, there's going to be a drift velocity. So if we measure our electrons down here, then on average, they're going to move this direction with some other velocity here. So when we apply a voltage, right, so these things are going like this, and it's totally random. There's no direction, no current flows because the motion is totally random. As we apply a voltage, then we get a different picture. Here, as we apply a voltage now, let's say that this is our negative side over here. So negative is over here. So negatives over here and positives over here. Now, when we put our electrons in here, they're going to be attracted this way. So they're going to be curved. They're still going to undergo a lot of collisions, but now on average, they will move back over this way. Right? So their paths are a little curved and it's tilted. So now it's not completely random anymore, and our electrons are moving this way. But this is only if we apply some voltage right here. That's going to create the current. And then that is also going to give us our current. So if we don't have a voltage, no current is flowing. And this can only happen if we have a complete circuit. Now, inside of our piece of metal here, remember that the electric field can still travel close to the speed of light. Electrons are much slower. And this velocity is, on average, about 10 to the minus 4 meters per second. So this is very, very slow, right? So the electrons really don't move that quickly. And if you think about it, all of our appliances are using AC current. So that means the current changes directions 60 times per second, right? So the electrons are going back and forth. And so they don't actually really move that much. So when you turn on your console, the velocity is not really that big, right? And so if you think about it then, electrons don't really travel in a straight line for very far, but they do move back and forth, okay? And so if you think about it, the electric field travels through the wire at about the speed of light. It's a little bit slower, but it's basically the speed of light, which is 3 times 10 to the 8 meters per second. So this is the speed of the electric field, which is the speed of light. And in physics, we always call that c. So as soon as you turn on the light switch, that electric field is immediately transmitted through the wire, and that's how it seems almost instantaneous that your lights come on. If it wasn't that way, you'd have to wait a pretty long time before those electrons actually made it from the light switch up into the light bulb. So when you turn on the light switch, the electric field goes through the light bulb, and the electrons that are already in the light bulb start to move because they feel a force from the electric field. So now we're tying it all together. The electric field travels through the wire. It creates the force on the electrons that are already in the wire. So the free electron gas is already here. And as soon as they feel that electric field, they feel the electric potential, then those electrons start to.
Thank you, like and subscribe down below.